vision sensors often is that they suffer from limited dynamic range. And so here in this video, I try to demonstrate the fact by taking a camera from indoor to outdoor environments. And on the bottom, I'm going to display a histogram of the intensities. And as you know, that as I make this transition from an indoor environment to an outdoor environment, the distribution of intensities right now, for example, is skewed extremely to the oversaturated region. And as I move later towards an indoor region, the distribution again skews a lot towards undersaturated space. Now, if I set auto exposure to be on, I still see similar issues. So here we've got state-of-the-art visual SLAM tracker, or SLAM, and I'm basically taking this camera outdoors. And note that the moment I look towards the sky from under a canopy, again, because of the rapid auto exposure changes, my tracker basically fails to continue to keep track of the features. So why does this happen? Most of the tracking still is dependent on Lucas-Canary tracking. And the way it works in there is that Lucas-Canary tries to estimate the parameter that best explains the difference between a current virtual image, which is warped for every single pixel, in the reference image, which is the term on the left, with a current live image, which is the term on the right. And we do this over all the pixels in the image. And so this here is the brightness constancy assumption that we make, which pretty much says that over small warps, we expect that the intensity of the pixels would remain the same. However, this is the exact fundamental assumption that's often violated in these dynamic lighting changes. So state-of-the-art tries to mitigate these issues by either tracking really fast, but as Handas mentioned in his paper, you start hitting signal-to-noise ratio issues as you keep sampling faster and faster. The other approach that people have used in the past is that they've tried to use robust outlier detection using a slightly weighted term in the iterative least squares in the previous equation, or by trying to parameterize the illumination by using an affine illumination model. But neither of these techniques really solve the problem at hand. And the solution that we think works for this is by treating the images as a distribution, a joint distribution of spatial locations and pixel intensities. And once you think of images in this way, you can then try to look at a different measure of divergence in the same Lucas-Canary tracking framework. And the mutual information serves as a very reliable divergence measure for exactly this purpose. And the key idea here is that instead of looking at absolute intensity values, you're now looking at relative comparisons between images. So you're not the first people to think about this. Mutual information is used a lot in the medical imaging community for multimodal registration for the exact reason that I mentioned before. And lately in robotics, we've seen some effort by groups in France for visual surveying, and most lately by Paul Newman's group for trying to estimate pose given texture point clouds. So how do we apply this for visual odometry? First, a quick reminder of how iterative Newton minimization works for visual odometry. It's given a particular cost function, you evaluate the cost, you then compute the Jacobian and the Hessian, you compute the update, given those Hessian updates and the residuals, and then you basically repeat this for a particular pyramidal level until you reach some convergence criteria. Now you then transfer it over to from a higher pyramid level to a lower, from a lower pyramidal level to a higher pyramidal level, which is basically going from a coarse to fine approach. So you start off with a very small resolution subsample image, and then you basically keep feed-forwarding the transform upwards. So let's look at computing the mutual information cross function here. And the key intuition when you're trying to use mutual information for visual odometry here, then is you're trying to explain how much information does knowing the pixel value for a particular location in a reference image gives you about the pixel value in the live image. And to explain that intuition, we work with a toy example. So here's the 6x6 reference pixel, and I've discretized it into two image values, so that's red and yellow. And I'm trying to track a live candidate image, which is displaced by one pixel in the U and the V direction. And note that the colors of the two discrete values for the live image are different, and this goes on to basically demonstrate the fact that the cost function does not really depend on the absolute values at all. So As a quick reminder, mutual information is the KL divergence between the joint of a distribution and its marginals. And so to compute mutual information here, we'll have to compute a joint 2D histogram for the discretized case. And that looks like that. Essentially, you're running through all the pixels and you're evaluating this histogram windowing function for each of these pixel values. And in this case, this histogram window function is simply a delta function, which gives you a value of 1 if the argument is 0 and 0 otherwise. So what that really means is that, say for example, I look at a particular case where I'm trying to look at a reference pixel value of red and a live pixel value of green. So I would get a value of 1 in that when I'm trying to compute the joint, only when there's simultaneously that particular color at the same point. And so in that small figure over there, I have dark squares represent all the cases, all the pixel location when that's true. And therefore computing the probability then is simply a matter of counting all these valid locations. And I can then do this for all other combinations of these discrete values. Since there are just 2 on each image, that just accounts to 4 possible combinations. And so I can compute these partial, this 2D histogram, and then throw that into the mutual information cost function, and sure enough, I get a scalar value. And so when now I consider this situation where my live image is correctly aligned with the reference image, I can follow the same process all over again, compute my individual components of the 2D histogram, and as expected, when the 2 images are correctly aligned, I get a much higher value of the mutual information. And just to be sure, we look at another example where the 2 images are misaligned, and after following the same procedure, we then see that as the 2 images are misaligned, we get a drop in the mutual information objective. So how does this work for real and complex images? So now incremental warps would often require subpixel interpolation, and if you're trying to throw this to an optimization function, we need a derivative that is available. So to do that in the histogram function, instead of using that discrete occupancy value, we use cubic B-splines. And what that allows us to do is that instead of giving a discrete 0, 1 value, it allows you to spread the information through. So for a particular warped pixel, you get 4 contiguous values that you would update in the joint histogram instead of 1. And for each of those 4 values, you have 4 values for the reference intensity value. So what ends up happening is that you update 16 bits for every single pixel. And now you can just run through every single pixel in your 2 images, and at the end of the day, you get a joint histogram that you can compute. And so this is what it looks like for a real-world image. And as you can see, you've got a clearly well-defined peak and smooth cross function, which makes it very viable for optimization. So the next part is computing the Hessian and the gradient. And there are a few computational optimization we need to make. Now, the first problem is that unlike a typical SSD tracking formulation, you have components of the currently warped image in your cost function. And that's because of that multiplicative term there. And the fact that your computation cost increases between every level means that we need to be smarter about how we compute these terms. So we do this in 3 ways. The first way is by we employ the standard inverse composition trick, where we now warp the reference image and then update the live image to move towards the reference image when doing the tracking. We exploit the structure of the derivative, and we exploit the coarse-defined nature. And I'll quickly run through what we do over here. So inverse compositional, essentially all it allows us to do is that instead of computing the gradient and Hessian in the inner loop, we can compute the Hessian before we run the inner loop, and that saves us a lot of computational time. Then in the derivative structure, note the joint histogram this is what it looks like with the inverse compositional, where now we only work with delta increments of the warp. So when we take the derivative, applying the chain rule, we only need to worry about the derivative of the second window function. And so first we take the derivative of the windowing function. That gives us a spline derivative, which we already knew was analytic. Then we get an image derivative, which again we can compute at the reference image. And finally we get a warp derivative, which is again computed at the reference image. So essentially for every Jacobian computation, all we need to do is compute the spline values at the warped image. And this allows us to compute things very quickly. Another thing we can do is that we can exploit the fact that image gradient is a multiplicative term, and so we only consider the high gradient pixels. And we perform non-max suppression to remove the redundancy in the data. What this basically allows us to do is that we only need to consider 10% of the pixels in the image, and that allows us to compute these values really fast. And finally, we exploit the fact that when aligning the images, we move from a coarse-to-fine setup. And so we exploit the fact that mutual information is more robust at the higher pyramid levels. And as we move towards the lower, higher resolution pyramid levels, we then move on to SSD to provide the fine-grained tracking. And that allows us to basically run at roughly 25 baud for 640 by 480 images. And so finding results. So on the left is basically a live video in which I'm basically ramping the light from bright to super dark. And in the middle, you'll see the current image tracked with respect to the first image in the video. And so mutual information tracks through that lighting disturbance very well, whereas SSD, the moment the lighting changes, it collapses horribly. And if we plot the per frame error, it turns out we get a 3 orders of magnitude per frame error difference. Similarly, when I do a local ramp, so basically I'm moving the light around, I see a similar sort of performance, so my mutual information tracks through, but the moment the overall global lighting changes for SSD, it fails. And finally, just as a proof of concept, I just do direct frame-to-frame visual odometry, and so by that I essentially mean, instead of comparing to the reference image, I just compare to the previous image. And I plot the data with respect to mocap in the bottom, so note that this is because it's pure frame-to-frame visual odometry, it's going to be drift. However, SSD jumps in a few locations, and this is like one such example of what happens. So note there's a very sudden light change and motion blur, but it still tracks through all of that. And so, in summary, we've shown that mutual information is a reliable cost function for robust visual odometry, especially when used in a keyframe context. And even though it's computationally expensive, we can use hybrid approaches to obtain real-time performance. And in the future, plan to add graph optimization and a keyframe-based backend, and perform faster pixel subselection for computing the cost. Thank you. And
yeah, thanks a lot. So very good timing, and we have time for a few questions before the coffee break. So, anyone has a comment, question? Yes, yeah.
I don't know if I missed something, but I was just a bit confused that you compute the Hessian just once, so outside of the inner loop.
yes,
Does it change a lot also in the inner loop?
yeah, so I mean, the main assumption that you're making when you're computing the Hessian once is the fact that you're going to have a small warp. And that's the standard thing that you need to, assumption you need to make when you're making the inverse compositional setup. Purely because, I mean, the depth information that you have is with respect to the reference image. And so the further and further you try to look away from the reference image, the more occlusions and the more missing data you have. So, yeah. Did that answer the question?
Okay, yes.
Okay.
Question? Yes, there. Laura.
My question is, have you compared your method with any other direct method for visual odometry, such as edge alignment? You know edge alignment for visual odometry?
Edge alignment? No, I've not. So, sorry. No, I've not compared it with full-fledged odometry pipeline simply because I still have to implement the backend. But I do compare with the baseline with the SSD-based tracker, which is what you would expect from any conventional direct tracking algorithm.
Thank you.
Another question? I may have one. Is about these days it looks like neuromorphic event-based cameras also are very promising, like really kilohertz or megahertz. Could you extend it to those as well, or?
So that's a very interesting question. And one of the things that I did mention early on is I feel that there are just two ways to solve this question. And the first is to just sample very fast. And event-based cameras are exactly doing that. It's just a complete paradigm shift. I guess I've not really thought too much into it. Technically, I would guess I could apply it to event-based cameras, but I think event-based cameras, just by the fact that they are intrinsically already measuring relative changes in intensities, the extra benefits of this algorithm might be missing. Yeah.
Okay, no, that's fine. Okay, very good. So let's thank the speaker again.